hear from Sophia okay, about small juvenile triceratops skull from the Hell Creek Formation in Montana. We'll get back to this, don't worry. So I'm going to start today with a quote by Peter Dodson, who's a paleontologist and an expert on the horned dinosaurs. And he said that anyone who can name a single dinosaur can name Triceratops. I'm going to take a safe guess and guess that most of you are probably not paleontologists, but I would be surprised if any of you had never heard of Triceratops. After all, they've been featured in everything from postage stamps to to blockbuster movies like Jurassic Park. And there are several reasons why this dinosaur is such an icon of the age of dinosaurs, and one of those is because of their great abundance. In the late Cretaceous, Triceratops is thought to have made up around 40% of all large-bodied dinosaurs in their area. And this is a lot of Triceratops living and dying. And the area where they were living and dying was along the edge of the Western Interior Seaway, which was a shallow sea that ran from the Gulf of Mexico all the way up to the Arctic Ocean. And where Triceratops lived along the coast of this was an area of active sedimentation. And it is these same sediments that were laid down 66 million years ago that are currently being brought back to the surface of the Earth in what we call the Hell Creek Formation. So the fossils of Triceratops and their contemporaries are being brought back to the surface in badlands in areas of Wyoming, the Dakotas, as well as eastern Montana. This is a small section of the Hell Creek Formation, and you can see that there are three main units, the lower, middle, and upper, and Triceratops is found throughout these three units. This has allowed paleontologists to create a stratigraphic survey, kind of a geologic timeline of Triceratops specimens within these layers. And this has also allowed them to begin to notice patterns of change within the skeletal anatomy, especially as you can see in the skull. So the skull is a very important feature for paleontologists. It is one of the more distinctive features on an animal, and so it is often used to classify an animal, to place it within its species. But Triceratops skulls did not only change over millions of years through evolutionary change, they also went through ontogenetic change, which is the change an animal goes through within its own lifetime. The main changes that we see in the skull of Triceratops have to do with their cranial ornamentation, so the horns and the frill. The younger Triceratops have short, stubby frills that are almost square when you look at them from above, and they have backwards facing horns. But as they grow older, these frills begin to spread out and thin until they eventually create those parietal fenestrae, which is just a fancy word for holes in the frill, and their horns actually switch from being curved backwards to being curved forwards. As you might guess, this can create some problems when it comes to identification, when the feature that is most often used to help identify an animal is also the feature that changes the most throughout that animal's lifetime. And in fact, Triceratops has had many problems with misidentification. Since it was first described in 1889, it has had 16 species attributed to it, and we're now down to 2 species, so that's quite a large change. But some dinosaurs do not have this issue. Some dinosaurs like Maiasaura, Montana state dinosaur, have been found in nesting sites, where everything from embryos within eggs to hatchlings to full-grown adults are preserved in the same area. So it's very easy to put many growth stages, many different ages of this dinosaur within a single growth series. And in fact, Maiasaura has one of the best growth series of any dinosaur that is often used as a baseline to compare to, because most dinosaurs do not have this wonderful contextual evidence that we get with the nesting sites. This dinosaur, for example, was until fairly recently thought to be 3 species, Dracorex, Stygimoloch, and Pachycephalosaurus. Current research suggests that this was actually just one dinosaur at 3 different growth stages. And like Triceratops, you can see that a lot of the change is in the cranial ornamentation as the dome gets a lot bigger and these spikes on the back of its head actually go through resorption, going back into the skull as it ages. We also see this in modern day animals like the cassowary, again, distinctive cranial ornamentation, but as we live alongside the cassowary, we don't have to worry too much about mistaking a younger cassowary for a different species. So the big question is, how do we prevent misidentification with animals that have not only been extinct for tens of millions of years, but that lack the kind of contextual evidence that Maiasaura has. A great place to start is an animal with a huge sample size. And horned dinosaurs have some of the best fossil records of any group of dinosaurs, Triceratops being no exception. In fact, 80% of dinosaur species are known by 5 or less specimens. That's all we have. But Triceratops is known by literally hundreds of specimens, which is great for exactly what we're doing, creating a growth series. There is one hurdle though, and that's that when you think of Triceratops, you probably think of something like this, a huge animal, big horns. Your mind probably did not immediately jump to something like that. So that's a baby Triceratops. And the reason why it probably didn't jump to this is because of a historical collection bias, where for a long time collectors were trying to fill museum exhibit halls with the biggest and best specimens they could possibly get their hands on. This often means that they looked over smaller specimens like this. And because of that, only 2 specimens from the earlier growth stages have been described this far. This being one of them, the smallest Triceratops skull that we know of so far. For reference, those horns are about 2 inches long. So this is a very young specimen. And the second specimen that has been described is just over twice this size. And for the most part, they represent a lot of what we know about early Triceratops growth stages. But in 2006, a Museum of the Rockies volunteer named Sonia Starf discovered a small juvenile Triceratops skull in the Hell Creek Formation near Jordan, Montana. And this was MOR 2569, which is the subject of my research. And MOR 2569 falls right in between our 2 previously described specimens, a little bit closer to the smaller specimen. And these highlighted bones are the ones that were found with the skull. But today we're just going to focus on 2 of them. The first being the post-orbital horn core. So post-orbital, that kind of means behind or above the eye. And then notice I said horn core and not horn, and that's because that's exactly what it is. In life, Triceratops had a keratinous sheath that was actually covering this horn core, and we got to it eventually. So this is obviously not from a Triceratops, but it's from a modern day cow actually. It is made of keratin, just like a Triceratops horn would have been made out of, and though it's from a mammal, not a dinosaur, it's likely fairly similar to what a Triceratops horn sheath looked like. The second item of cranial ornamentation that we're going to focus on is the frill. So the frill is made of 3 different bones, the parietal in the center, and then the squamosals, one on each side. And it has a lot of interesting information to tell us, the first being bone texture. So this is the parietal, again, just the center bone of the frill. And this light gray that you see around the edges and then the center, this is long-grained bone texture, which is a striated texture that we find in bone that was still growing when the animal died. So we would expect to find more of this on either younger animals or animals that are still going through a lot of change within their bone structure. The second bone texture, the dark gray, this is mottled bone texture, which has lost its striation and it is in fact going through resorption. There is also a third bone texture called rugose, or adult bone texture, that we don't see any of on this specimen because it is such a young skull. And hopefully in the future we'll be able to make bone texture maps of frills for every growth stage in the Triceratops growth series. Also on the frill, we found these 2 marks, which are tooth marks, and they belong to a carnivorous dinosaur. We don't know if they were, if it happened before death, maybe as a cause of the death of this animal, or afterwards, maybe through scavenging, but either way, they are a great look into what predation or consumption of Triceratops was occurring by other dinosaurs. So, learning about how the cranial ornamentations of Triceratops changed and developed as they grew can give us insight into how they may have behaved or interacted with each other. So today, we're using the bone texture of the frill to determine relative age, but 66 million years ago, Triceratops was probably using the size, the shape, or maybe even colorful patterning on the same frill to communicate things like age, sex, perhaps their mood, or even individual identification. And the huge sample size of Triceratops, as well as the incredible variation between individual specimens, has allowed us to create a very well-researched growth series. In fact, one that, like Maiasaura, can be used as a baseline, not only to learn about Triceratops, but how all dinosaurs grew and developed. The MOR 2569, the specimen that we're researching, has filled in one of the growth stages of the Triceratops growth series. And it has both answered some questions and also raised some new questions, but every specimen from big Triceratops with 8-foot skulls to the little tiny baby Triceratops with 2-inch horns answers a lot of new questions and gives us new information not only about Triceratops, but all dinosaurs. And even though this is one of the most well-known dinosaurs, we still have a lot to learn about the behavior, the life, and the growth of Triceratops. And lastly, I'd like to, oh, maybe not lastly. Well, I'd like to thank a few people, everyone who put on this colloquium, and thank you all for coming. I'd also like to thank Dr. John Scannella, who's my mentor, for helping so much with all of this, as well as Jack Horner, Lee Hall, many other people who studied Triceratops before me or allowed me to study this specimen, and also the United States Fish and Wildlife Service as the specimen was found on their land. So, thank you. And if anyone has questions.
Yeah, we definitely have time for a couple questions here.
Yeah.
How far apart are those?
They are about, I'd say maybe an inch or within an inch or two apart. They're fairly close together. And they have actually found tooth marks similar to that on frills of other Triceratops specimens, actually of different ages. So there's more research going into that as well.
Was it only the skull that was found in this discovery, or was it found with any other bones that had teeth marks on them?
Yeah, so it was only the skull that was, only the partial skull that was found with this specimen. And it does have some bones in the skull that are the smallest elements ever found. So even though there's a smaller skull, it is missing some of the elements that we do have in this skull.
First, great talk. Thank you. I learned a lot. And apologies if you mentioned this, but I wondered the bone texture.
Mm-hmm.
How was that generated? Is this with like a CAT scan? And then how are new sort of techniques changing how people look at these and try to draw out similar information?
That's a great question. So the bone texture is actually, it's usually, you can just see it with your naked eye. The striations and the modeled bone texture are pretty easy to differentiate. And there has been work done before with bone texture on other ceratopsians, specifically on centrosaurians, but this is a chasmosaurian, so this is, it's interesting that we're seeing some of the same patterns that we see on centrosaurians on this